Thank you. Gogh Imaging is a software company, and our expertise in 3D computer vision, which is what I want to talk about mainly today. So in the world of augmented reality, we're starting to see a lot of interest in applying real-time 3D computer vision to augmented reality. I want to talk about why that is and why it's important, and what some of the future holds for computer vision. So just give you a background, Gogh's been around for about 7 years. We worked on a number of different 3D computer vision projects, anywhere from medical to parts inspection to weighing livestock, which was one of our projects using Kinect sensors, and to 3D printing. We worked with a couple of 3D printing companies to improve their sensor technology or 3D modeling technology. And most recently, we're getting a lot of interest in the augmented reality, mixed reality applications. So there are, quite a few different type of augmented reality applications. The key technology involved in augmented reality or mixed reality or what have you is pose estimation and tracking. So instead of what we want is application to be able to understand its pose relative to the scene or objects around them. Now, once it does that, then you can do a lot of cool things, like some of the things that Intel showed the last presentation. Now, to do this really easily and seamless is very difficult. That's where I think the 3D computer vision technology can come in. We're still at the very early stage of that to make it really easy to use. It's still, but we're working through the problem, and I think industry's made a lot of progress over the last couple of years. I think we'll get there within a fairly short time frame. So there, either whether you use a smartphone, tablet, or something like HoloLens from Microsoft or Oculus or what have you, what you need is some kind of way to tie the application's position and the pose relative to the scene and the object, right? So always coming back to that. So currently what we use is markers. So markers are pretty good, and it works pretty well. It's reliable. Problem is, my biggest problem with marker is that marker does not have any relationship to the real world. Okay, you put a marker there, you don't know where the marker is relative to the objects around them or those features around it. So this is quite limited in terms of what you can do with markers. And putting markers on objects is not that easy either. And then if you have 100 different objects, you got to put markers at the exact same position in every object. That's not easy. So all those become a problem. Then you go, well, why don't we use 2D computer vision technology? Well, 2D computer vision technology uses 2D features, edge detections or RGB information to gain a tracking information or pose estimation. And but problem with 2D is it's not as it works in some cases, but it's not as reliable as 3D. So when I talk about 3D computer vision includes 2D. Okay, so it's 2D plus depth processing. So yeah, 3D is much more reliable than 2D. There's no argument. Okay, so when we get to real-time 3D computer vision, we can now use depth information to get the surface normals. We can look at the shapes of the objects. We can look at the scales, dimensions, measurements. All those can help you handle occlusions, dynamic nature of the scene, dynamic nature of the moving objects. We can handle those much better using 3D computer vision. And great news is a large number of companies, including Soft Kinetic and especially Intel recently, been pushing the low-cost 3D depth sensors out onto the market, and a number of computing platforms are adopting them. So you can actually go out to the Microsoft store right now and buy computers with the built-in 3D sensors. There aren't any applications for it yet, unfortunately, because it just came out. But there are quite a few companies working on these applications. So there are literally millions of devices being shipped right now with the real-time 3D sensors, which could be a news to some of you. But and then there are other companies. There are a bunch of new companies coming out with new sensors with improved accuracy and resolutions. So typical augmented reality system using 3D computer vision processing. It has hopefully our Starry Night middleware built in to the system, but something similar to that, and it can be embedded. So our Starry Night consists of 4 parts. First is SLAM, or what we call dynamic SLAM, a SLAM that can handle dynamic scenes. When the scenes change, SLAM automatically makes corrections to the scene model. So that's what we call dynamic SLAM. Second, we have object recognition. We can break the scene down into objects and features and recognize them, but also track them. We also have an automated 3D modeling process, because what you want is after you extract that object, you want to get a 3D model out of it, because once you get the 3D model, you can do a lot of other things with that. And then finally, you need the analysis model to analyze the object. Respect to augmented reality applications, first 2 is the key parts respect to that. So hopefully this video plays. Okay, so this is scene tracking, where you track the scene, and at the same time we use Fusion to capture the scene as a 3D model. So once you capture the scene, you approach the scene, and you can track, and all of a sudden when you change the position of the application, then you can regain tracking right away, and then you can continue. So this allows once again, it's all about pose estimation and tracking. This is our object tracking, which is, we just put a little, flying ducky augmented reality on top of it. It tracks the object as the object is moving, and you could be moving relative to the object as well. What it does, it accurately tracks the position and the pose of the objects, so you can superimpose the graphics on them. So challenges are, number 1, computation. But we've been able to, and I think other companies have done as well, to run the first part, the SLAM portion, at 20 to 30 frames per second, even on mobile devices, only using CPU. We haven't even gone to GPU, and we are already able to do real-time SLAM in 3D. And on top of that, our object recognition can do 60 frames per second tracking mode. So we're pretty much there. Next step for us is go to GPU to get even faster processing. So the large data set has always been a problem. But we've been able to break the scene down into small boxes, be able to process them very efficiently. One thing that I don't have on this slide, which I want to mention, is that one of the other biggest challenges that most of the current 3D sensors are not, but are noisy, a bit noisy. So that causes problems. So we spend a lot of time and effort on our side, algorithmically and what have you, to overcome those deficiencies. And for the most part, I think we've done that. So overall, we're demonstrating our what we call the dynamic object generator module tomorrow at the booth. What it does is you take an object, okay, you hold it in your hands, and you move it around. It will dynamically create a 3D model. At the same time, use that to generate a reference model, and use that to track this object in real time. Okay, and we'll be demoing that at our booth tomorrow, if you could stop by. So, thank you. That's it. Questions?
Can you generate high-quality texture after the constructed imaging?
Our quality of our texture is as good as what we can get. There are methods to get photorealistic texture. We're not there yet. So, but there are definitely ways to get that photorealistic texture, even with the noisy scans. But no one has that quite yet.
That was shown in the video. I saw seems like you are using the structural sensor to reconstruct the mesh.
We use both the structure as well as the time of flight. The both results are both pretty good. We get some pretty good results from both. I think there was a.
Yeah, quick question about the 3D compute type expense. Is that before or after generating the 3 to 5x? Is that before or after generating the depth? Does it include generating the depth map information from the sensor or?
Yeah, the depth information generation, typically we see somewhere between 10 to 15% processing overhead to get the depth information. Generating, running the sensor company standard SDK. Yeah, so it's not huge. Yeah. Thank you. Thank you.